Welcome to Chapter 9. In this chapter, we'll discuss the principles of pipelining. So, pipelining is by far the most important technique for improving the performance of processors and speeding them up. So, there's no other technique that is, much more that is more important than pipelining. So let's discuss this technique in a fair amount of detail in this chapter. So this chapter is fairly long. We have 125 slides. So the discussion will be spread across several lectures. Again, this is a chapter of the book Computer Organization and Architecture, written by myself, Dr. Sarangi from IIT Delhi. It has been published by McGraw-Hill in 2015 and should be available in almost all locations worldwide. The way we divide this chapter is as follows. We'll have an overview of pipelining first. Then we shall discuss a pipeline data path where we change the data path of the processor to incorporate pipelining. Then we'll discuss several problems with pipelining called pipeline hazards and methods that we apply to fix those problems, pipelining with interlocks and forwarding. We then look at performance metrics for processors and finally end with a quick discussion on interrupts and exceptions. So up till now, we have discussed the design of a simple processor to execute the simple RISC instruction set. We have looked at two kinds of styles. We have looked at a processor with a hardwired control unit, which is faster. And we have also looked at a very flexible processor in which even the implementation of instructions can be changed. So it's called a processor with a microprogrammed control unit. So we have taken a look at a microprogrammed data path, a microassembly language, and micro instructions. So we'll in this chapter only be working with processors with a hardwired control unit, which is processors of the first type, which are by far the most common. So we'll only work with this and try to increase the performance of such processors. So let's look at how to design efficient processors. So we'll only look at hardwired processors here. So what we claim is that there is a lot of waste in the sense there is a lot of idling inside the processor. Most of the time, a lot of stages inside the processor are doing nothing. For example, what is the IF stage doing when the MA stage is active? Well, the answer is it is doing nothing. It's just idling, right? So it's absolutely idling and it's doing nothing at all. And similarly, what is maybe the EX stage doing when the MA stage is active? So then also the answer is that it is idling and it is doing nothing at all. So this tells us that if there are 5 stages, only one of the stages is active at any instant of time. These are the 5 stages, right? And only one of these stages is active at any point of time. And let's say if this is active, the rest of the stages are not doing anything. And this to us represents a source of inefficiency, which if removed can possibly give us more performance. So let's look at the notion of pipelining. So let's go back to our basic example, which is a car assembly line. So the question is the engine shop idle when the paint shop is painting a car? Well, the answer is no. So when we are painting one car, the people at the engine shop are essentially building the engine of another car. So when this engine goes to the body shop, what does the engine shop do? It builds the engine of yet another car and so on. So the insight is that multiple cars are being built at the same time, right? So and pretty much a half-built car proceeds from one stage to the next. So let's maybe draw a diagram. So let's assume there's a part of the factory, part of a car factory that's working on the engine. And then this part of the car factory, let's say, works on the body. And this part of the car factory works on the paint. So once an engine moves from the engine shop to the body shop, well, the engine shop does not idle. the workers start building the engine of another car. Similarly, the moment the body of a car has been made, the body shop is not idle. Instead, we build the body of another car. So, can we use the same logic in a processor? We shall see. So, let us consider a example of a pipeline processor. So, let's look at our 5 stages: instruction fetch, operand fetch, IF, OF, execute stage EX, memory access MA, and register write RW. So these are the 5 stages: IF, ID, EX, MA, and RW. And the stages process 5 instructions simultaneously. Let's assume that this is the case. So this will be similar to a car factory, where a car factory also has multiple shops, and a half-built car moves from one shop to the next. But no shop is ever idle. So one shop is building the body for one car, another shop is building the engine for yet another car. So if we straightforward bring the analogy over here, this is what we get to see. That if we divide our processor into the 5 stages, we can have one instruction in the RW stage, one instruction in the memory access MA stage, one in the EX stage, one more in the OF and IF stages respectively. One more in the OF, one more in the IF. So we can have 5 instructions. So the earliest instruction would be in the later stages. So this would be the earliest, and this instruction would be the latest. And as an instruction's fetch is over, it will move to the as IF is over, it will move to the OF stage, and as operand fetch is over, it will move to the EX or execute stage, so on and so forth. So this process is known as pipelining. It might sound simple, but it's incredibly complicated. So let's first take a look at what is the advantage of pipelining. So the advantage of pipelining is that we are keeping all the parts of the data path busy all the time, right? So in this case, if I again go back, what we get to see is that if in the data path we have 5 stages, the 5 stages are busy all the time, right? So basically similar to a car factory, no part of a car factory is actually idle, and same is the case here, that all the stages are busy all the time, and one instruction process finishes its execution in one stage, moves to the next stage, finishes execution here, moves here. So if you have 5 stages, we'll have 5 instructions being processed simultaneously, and then at the end of the processing, one of the instructions will move out, the second instruction will come here, the third will come here, and a new instruction will enter the fetch stage. So the idea sounds simple, but the question is, where is the advantage? So let's see. So we'll have a much deeper discussion on the advantages of pipelining towards the end of the chapter, but let's at least get an initial preliminary idea. So let us assume, so this is a simplistic assumption, it's regularly made, that all the 5 stages do the same amount of work, right? If you make this assumption without pipelining, so let's assume that the same amount of work means t seconds of work. So without pipelining, every t seconds an instruction will complete its execution, right? So which means that if an instruction enters the processor here at t equal to 0, after capital T seconds, the instruction will get out. Which get out means it will have finished its execution. So means that it will if it's a memory instruction, it will finish the memory access, and if a register needs to be written to, it will write to the register. So it will essentially complete the work of all the 5 stages. So with pipelining, what is happening, that instead what we have done is that we have broken down this circuit into 5 parts: part 1, part 2, part 3, part 4, and part 5, right? So in 1, 2, 3, 4, 5, what we see is that in every t by 5 seconds, right, in every t by 5 seconds, because now remember that since we have broken down the data path into 5 parts. So basically every part will take, instead of t seconds, it will take t by 5 seconds, which basically means that, for an instruction to move from here to here, it will take t by 5. To move from here to here, it will take t by 5, and so on and so forth. Right? So basically, which means that if for somebody who's standing over here, so consider an observer who's standing over here and looking at what's happening, the observer will see that every t by 5 seconds a new instruction is coming out. Right? But if the processor was not pipelined, and the observer is standing over here and the observer is looking, what the observer will see that one instruction enters at t equal to 0. At t seconds, it finishes. In a sense, it comes out. Then again, one more instruction comes in. So every t seconds, one instruction comes out. And in this case, every t by 5 seconds, one instruction comes out. Which means that, let's say, after n seconds, the number of instructions that would have successfully executed in a pipeline processor is n divided by t by 5, which is 5n by t. But here, after n seconds, the number of instructions that would have completed is n by t. So a pipeline processor in this case, in its most simplest form, can process 5 times more instructions than a non-pipeline processor. All right. So that's the basic idea, that that is where the expected speed up will come from. That it can process more instructions at the same time, and also if we are looking for an observer who is looking at a pipeline processor from outside, every t by 5 seconds a new instruction is coming out. So I'll just go back to that diagram. Every t by 5 seconds a new instruction is coming out. So the rate of instructions coming out is 5 times more as compared to a non-pipeline processor. As a result, if a program has n instructions, then it will execute 5 times faster. All right. Now let's take a look at the design of a pipeline. So the first thing that we need to do is that we need to split the data path among the 5 stages, in a nice and clean way. So we need to divide it into 5 paths, such that each part can contain a separate instruction. So regarding the timing, what we need to do is that we need to insert latches. Well, they are not latches, they're actually flip-flops, because they are contained by because they're controlled by a clock. So we'll also call them pipeline registers, or just registers. Well, but just registers will confuse us with register in the register file, so let's call them pipeline registers. So they will also be latches, but by latches here we mean that they are also connected to a clock. So there's a little bit of an abuse of the symbols here, the little bit of abuse of the naming here. But it should be clear from the context. So these pipeline registers or pipeline latches, let us add them between consecutive stages. So we will add 4 latches. What we'll do is we'll have if, then the if stage will write its result to a set of flip-flops that are controlled by a clock, a set of pipeline registers. Then we'll have the OF stage, again a set of pipeline registers or pipeline latches. Then again the EX stage, the same thing, MA stage, and the register write stage RW. So what we shall see over here is that we are adding 4 pipeline latches. So let's call this the IF-OF latch, because it's between the IF and OF stages. Similarly, we'll add an OF-EX latch, an EX-MA latch, and an MA-RW latch. So these latches are actually controlled by a clock. See, if this is the clock, so the clock goes to all the 4 latches, here, 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 and here. So it goes to all the 4 latches. So the way we design it is that at the negative edge of a clock, one instruction which is in one stage will move to the next stage, right? So at every negative edge of the clock, instructions move from one stage to the other, one stage to the other, one to the other, and at the end, they go out of the pipeline, means that they finish their execution. So this is what our new diagram looks like, that we have these pipeline latches. So mind you, again, a latch here is actually a flip-flop. It's controlled by the negative edge of a clock. So we add 4 latches between the stages, and every negative edge, the instruction that is being processed in this stage moves to this stage. Every negative edge instruction here moves here. So we add a latch between subsequent stages, and the latch is triggered by the negative clock edge. So what is it that travels between the stages? We have already answered this in the previous slide, that the instruction packet travels. So what exactly is the instruction packet? Well, the instruction travels, it's an instruction packet, but what exactly is in there? So we have the contents of the instruction, which means the instruction itself, right? It's 32-bit contents. Then the program counter that is associated with the particular instruction. All the intermediate results that we compute, and all the intermediate results we compute, and the results that are required in the subsequent stages, they also move along with the packet. And all the control signals that we require to control the multiplexers in the subsequent stages. So basically every instruction will move with its entire state such that there is no interference between instructions. So previously what was happening is that the control unit, previously what was happening is that the control unit which was there in the OF stage was sending the control signals to, well, it was actually dotted lines. Let's see, let me remove this line. The control unit was sending control signals to all the stages, right, EX and so on. But in this case, this is not possible. The reason it is not possible is basically because we have 5 instructions. So the control unit generates the control signals for which instruction? So either we need to have 5 control units, which is not a reasonable idea. So what we do is that when an instruction passes from the IF to the OF stage, it collects all the control signals that are required in the subsequent stages. That is a part of the overall instruction packet, right? Let's call it inst packet. And the inst packet moves from stage to stage, right? So in some stages, some information is removed. In some stages, some information is added. But broadly, the instruction packet moves. And what does it contain? It contains the contents of the instruction, right? The 32-bit representation of the instruction. It contains the program counter, the PC. It contains all the intermediate results that would be required in the subsequent stages. And it contains all the control signals that are required to control multiplexers in the subsequent stages. So this is the entire state of the instruction that moves across stages. So let's look at the design of a pipelined data path. So almost everything remains the same. I would suggest that the readers take a look at the IF circuit that we had designed in chapter 8. So they will find that the circuit is the same. So there is absolutely no change. It is just that we have this extra green box, the IF OF register between the IF stage and the OF stage. So it's the pipeline latch or the pipeline register. We'll use the terms interchangeably. So what we store here, we store the program counter because we want this to, so this is a part of the instruction packet. We store the program counter and the contents of the instruction. So this is pretty much what we store over here. And this is what moves to the next stage. Let us now consider the OF stage. So OF stage begins from the IFOF register. What did we get from the previous stage? We got the program counter, the PC from the previous stage, right? So this is what we got. And we got the instruction packet from the previous stage. So this is one more thing that we got from the IF stage. So after this, the rest of the circuit between the two green boxes, between the two pipeline registers, is exactly the same as what was there in the non-pipeline processor. So it is just that was drawn vertically, this is being drawn horizontally, that's the only difference. But otherwise, the entire circuit is the same, but let me nevertheless re-explain. So first is that the instruction goes to the control unit, and the control unit generates all the control signals. The control signals are a part of the instruction packet. So they flow along with the instruction. So this is stored directly in the next register, which is the OFEF register, because it's the OF stage and it's the EX stage. So the OFEX pipeline register, pipeline latch saves the control signals. Simultaneously, control unit quickly generates the two control signals is store and is ret. If you would recall what had been done in chapter 8. So my advice is that before taking a look at this chapter, please take a look at chapter 8, the processor design part. So you can either read the book or take a look at the video and then come back. So what we had designed in chapter 8 is that for the register file had two read ports, two interfaces. The first read port read the first source register or the return address depending upon the isret signal, and the second read port based on the isStore signal either took in the contents of the RD register or the second source register, which is RS2. Then the register file, we have two outputs. We have OP1 is one output and OP2 is the other output. So OP1 we directly save in the pipeline latch and we call it A. Simultaneously, we save OP2. So OP2 we also save it in the pipeline latch. We call it OP2 only. Also, we choose, so depending upon the value of the is immediate control signal, whether it has an immediate or not, for the second operand we choose between IMEX, which is the extended immediate, and the second source. So basically, depending upon the is immediate flag, we choose one of them, and we refer to this as B. Alright, so why are we doing this? Because if the is immediate flag is 1, it means that the second operand is an immediate. So we should take the input from here. And if is immediate is 0, it means that the second operand is a register. So we should take the input from here. So in any case, this is saved as saved in the field B, and the first source is saved in the field A. We additionally save OP2 as well. The reason we save OP2 is that we will require this, and we will require this because this is the store operand. And so there's a special case being made for store. So let's see why is the special case being made. So in the case of a store, the idea is that we will have so let's take a look at a store instruction once again. So let's see, we will have in this case two registers, two source registers, and also we will have uh, one offset. So basically we will store into register RD. So mind you, for a store the path is like this, that we store RD, we read the result of RD, and the result of RD is basically the value that needs to be stored, which comes in over here. But also mind you, the immediate flag is 1 for a store because the immediate stores the offset. and which we add to the base register, which is RS1. So basically the immediate also needs to be stored. Since the immediate flag is 1, so this will not get stored, the immediate will come in. So that's the reason the store we will require both OP2, which is the contents of RD. So let me maybe use a laser pointer. So we will need OP2, which is the contents of register RD. So that needs to be stored, right? So that will flow via this route, because if is store is 1, then we will access the register file with the contents of RD, which is the destination register. So recall the special case that we are making for the store instruction. Then we read that and we store OP2 in the OP2 field. And then we store the first source register, which is coming via this route. So we will store that in the field A in the instruction packet. And also in the case of a store, the is immediate flag is actually true. Since the is immediate flag is true, uh, we will choose the immediate as the output of this multiplexer, the extended immediate, and that will be stored in field B. So now the question that can arise is, why do we store OP2 and B separately? Well, the answer is because for a store, OP2 will not be chosen by this multiplexer, but we still need the value of OP2. So since we need the value of OP2, we better store it separately for the store instruction. For others, this problem does not arise. So recall that we made a special exception for a store instruction because we didn't want to add an extra instruction format. So that's the reason we store the immediate in B, we store the source register in A for a store, and we store the register RD, which actually contains the data that needs to be stored, in OP2. Right? So the contents that need to be stored are stored in OP2, and the rest contain the immediate and the base register respectively. For other instructions, this problem is not there. So basically, A contains the first source and B contains the second source. The second source can either be the contents of a register or can be the immediate. So we again pass the instruction itself from this latch to this latch. We compute the branch target in the branch unit over here in the OF stage. The branch target is also part of the instruction packet, and the PC is also part of the instruction packet. So this is pretty much all the information that is going to the next stage, which is the EX stage. So we don't need anything else from the OF stage at this particular point of time. So those who have, those who would recall in chapter 8, we had designed the processor exactly in the same way, no difference at all. But the only difference is we didn't have these green boxes. We did not have the pipeline latches, so we were not storing intermediate values. In this case, what are the intermediate values that we are trying to store in the pipeline registers? Well, the intermediate values that we are trying to store are B, A, and OP2. These are values which have either come from the register file or from the immediate unit. So let me again erase everything and show you once again. So the intermediate values that we are storing, which are B, A, and OP2, have essentially come from the register file or from the immediate unit. So that's the reason they are being stored in this register. Along with that, we are storing control signals, the contents of the instruction, and also the branch target and another intermediate value. So that's also what we are storing. And the PC also passes, along with everything else, it passes to the next stage, which is the EX stage. So in the EX stage, these are all the fields that we get from the previous stage, which is OF. So we get the first ALU operand, which is A. We get the second ALU operand, which is B. And in the case of a store, the data that needs to be stored is in OP2. And the rest is all normal stuff, the instruction, the control for the instruction, the branch target, and the PC. So some of the control signals we route to the ALU. The ALU does its job. and ALU stores the result in the ALU result field of the EXMA pipeline register. So EX stands over here, MA stands over here. So the results of the ALU are stored in the field ALU result, and the OP2 we just move to the next register. And then the ALU also updates its flags, and this is processed by the branch unit. The branch unit gets control signals from the control unit. Is BQ, is BGT, and U is U branch. So just go back to the relevant part of chapter 8. So what the branch unit produces is that it produces the control signal is branch taken, which needs to go to the fetch unit. And also we have a multiplexer that chooses between the branch target that comes from the previous stage and the contents of register A, which will contain the return address in the case of a return instruction, right? So in the case of a return instruction, the contents of the field A will contain the return address. Otherwise, it will be the branch target. So using the isret control signal, we choose between them to compute the branch PC. So these are then sent to the IF stage, to the fetch unit, to the IF stage. Right, so this is one case where something is actually flowing between stages without going via registers. So we shall see this is an exception. So in this case, the is branch taken signal and the branch PC both are going to the IF stage, but all the rest of the intermediate results are being written to the pipeline register at the end. So that includes, that includes the control signal, contents of the instruction, the data that needs to be saved, which is in OP2, and the ALU result. Now we go to the next stage, which is the MA stage, the memory access stage. So the memory access stage is simple, no rocket science here. So it stands between the EX stage and the RW stage. So the ALU result contains the address, so this goes into the memory address register. OP2 contains the data that needs to be stored, so it goes into MDR, memory data register. Then the memory unit works, it interacts with data memory, it's controlled by two control signals, is load and is store. And the result of the memory unit is stored, in the case of a load, it is stored in the field called load result in the MARW register. So load result contains whatever we loaded from memory, and the rest of the fields just continues, the program counter continues. The ALU result that we had computed, the same thing is written in this register, the instruction and relevant control signals. Now let's move to the last stage called the RW stage. So the last stage is exactly the same as what we had in chapter 8. In fact, all the stages are exactly the same as we had in chapter 8. No difference at all. And so here it's just that we have drawn it differently, so it looks slightly different, but it is the same. So you recall we had a 3-input multiplexer that first read PC plus 4. PC plus 4 is essentially the return address which the call instruction will use. Then we had the load result and the ALU result, and it was being controlled by two control signals coming from the control unit, is load and is call. So then the one of the three inputs becomes the data that needs to be written to the register file. So this directly goes to the register file. The register file can be located either in the RW stage or in the OS stage, but the OS stage is a better place. So essentially it goes to the register file in the OS stage. Now we had one more multiplexer that chose between the RD field and the RA field, for the call instruction. So basically the is call control signal chooses between these two values, whether we write it to a register destination or whether we write it to the return address register depends upon whether the instruction is a call or not. because a call instruction writes the address of the next instruction to the RA register. So we make this choice and pass it to the address field of the register file, which tells it which register to write to. And we use the is write back control signal to enable a write. So we have seen all of this. All of this we have seen in chapter 8. The only addition is the green box. So all our control signals come from the green box. Previously they used to come from the OF stage. And here also all our values come from this pipeline latch over here and not from other stages, right? That's the only difference. So if I just summarize, this is a diagram of the entire processor. So there is no so there should be no ambiguity because this is exactly what we have seen earlier. The only differences are these green boxes where we store the temporary values and these flow from latch to latch to latch, and at every stage we do some processing. So the idea is that every stage we read the inputs from this register, and then what we do is that we do some processing and write the outputs to the next register. Similarly, in here also we read the inputs and write the outputs to the next register, so on and so forth. There are only two instances. So this is a normal flow of action. So the flow of action is that we have this one green box, which is a pipeline latch. At the beginning of a clock cycle, which means at a negative edge, we get data from the pipeline latch. We have a cloud of logic which essentially processes all the data, and we can access memory elements as well. Then all the results of this activity are written to another latch, and we then finish. There are only two instances where data is directly sent between stages. So one is the case of a branch in a taken branch, where the fact that the branch is taken and the new target are sent from the EX stage to the IF stage, right, using these wires. And the other instance is when we write to something in the RW, in the register write stage. So that is when all the values, if you see, essentially this is like a wormhole in Star Trek. So I didn't want to draw a long wire, so pretty much the values enter here and they come out here, which is same as taking a wire and going all the way here. And it's just that I didn't want to draw that many long wires, so I used this convenient trick. But essentially, when we are doing a register write, the ID of the register, the data, and the fact that we are writing these pieces of information need to go from the RW stage to the OS stage. So these are the only two instances in our data path where something flows, some kind of data flows between stages without going via pipeline registers or pipeline latches. So these are the only two examples, and they need to be kept in mind. The rest of the circuit is the same. The previous diagram was pretty complicated, so we shall not be using that in most of our discussion. We shall rather be using this diagram, which we call an abridged diagram. So the abridged diagram is fairly easy. We have the fetch unit over here and the instruction memory. So basically we just use one arrow to show all the contents that are transferred to the IF-OF register. The OF stage, we have three units: the control unit, the immediate branch unit, and the register file. So we have a single multiplexer over here to choose between the register operand and the immediate operand. And also for the special case of the store, we store OP2 separately in the instruction packet. In the EX stage, we have some information that flows back to the IF stage. So as we had mentioned in the last few slides, there are only two instances when information flows between stages without going through pipeline latches. So both these examples are shown in red. So the first case is when taken branch information, flows from the EX stage to the IF stage. So the EX stage additionally has the ALU unit, the flags, and the ALU result is written to the EXMA register. There is one connection between the inputs to the ALU unit and the branch unit. This is for the return address. Then we have the EXMA pipeline register and the MA memory access stage. The memory access stage simply communicates with data memory and writes the result of load instructions to the MARW pipeline register. And finally, we have the register write unit. So this is the second instance when information flows between stages. So basically from the RW stage, we have a connection to the OF stage where register write values flow to the register file. So we shall mainly be using this diagram because this diagram is way simpler than the previous diagram, which is far more complicated. So we shall mainly be using this diagram and we shall keep on making small modifications to this. Alright, so now that we have seen the basic organization of a pipeline, so let's take a look at some of the problems that can happen. So these are called pipeline hazards. So let's take a deeper look at pipeline hazards and then we shall look at different methods of fixing them or taking care of them. Alright, so let us consider the correctness and of executing programs. So let us introduce a new tool called a pipeline diagram. So a pipeline diagram is an analytical tool for us. So it will be shown in this fashion. So essentially the columns in the diagram represent clock cycles. The clock cycle 1, 2, 3, 4 to 9. And the rows represent the pipeline stages. So IF, OF, EX, MA and RW. So what this indicates, so basically if you see there are these cells, there are these square shaped cells. So what we are essentially saying is that instruction 1, which can be of the form add R1, R2, R3, enters the IF stage in cycle 1. Subsequently, it enters the OF stage in cycle number 2. It enters the EX stage in cycle 3, the MA stage in cycle 4, and finally the RW, the register write stage in cycle number 5, and then it exits the pipeline. So it finishes its execution and it completes. Similarly, we have instruction 2. So this instruction enters the pipeline in the next cycle. So it enters the pipeline in cycle number 2. Subsequently, it proceeds. So it proceeds to the third cycle, which is the OF stage, to the fourth cycle, which is the EX stage, the fifth cycle, which is the MA stage, and then in the sixth cycle, it reaches the RW stage, and the same is true for the third instruction as well. So we can see that in this pipeline diagram, all the instructions proceed diagonally towards the bottom right. Alright, so this is the main tool that we shall be using in for our discussion of correctness of programs inside pipelines. And a pipeline diagram is pretty much a matrix, but we don't show all the cells of the matrix because they are not required. So what we'll show is some of the cells of the matrix, and pretty much an instruction enters the pipeline diagram at the IF stage, and at every subsequent cycle it moves to the next row. Right, so we shall see there are some conditions on when an instruction can move and when an instruction cannot move, but this is the basic idea. So what are the rules for constructing a pipeline diagram? Again explained textually. So it has 5 rows, 1 per each stage. The rows are named by the stage. Each column represents a clock cycle, and each cell represents the execution of an instruction in a stage. So it is annotated with the name or the label of the instruction, and instructions proceed from one stage to the other across subsequent clock cycles, consecutive clock cycles. So let us take a look at one more example. Which is so this is add R1, R2, R3, then a subtract instruction and a multiply instruction. So let's take a look at this example in a different way now. So there are no dependencies across the instructions, in a sense that there is no dependency between the first, the second, and the third instructions. So pretty much the instructions can operate independently of each other. But since our pipeline can read in one instruction every cycle, so in the first cycle, one instruction will get into the pipeline. In the second cycle, one more instruction. Third cycle, one more instruction. So the crucial thing is that in each cell, only one instruction can be there. You cannot have two instructions in one cell. That will be tantamount to saying that in the same stage there are two instructions, which is not possible. Alright, so now let's take a look at some of the problems that can happen. Some of the problems that can happen will be explained like this. So let's consider a sequence of two instructions, instruction 1 and instruction 2. So let the instruction 1 be add R1, R2, R3, where we add the contents of R2 and R3 and we transfer it to R1. Then let the next instruction subtract R3, R1, R4, take the results of instruction 1 and use that as an operand. So here essentially instruction 1 is writing to R1 and instruction 2 is reading from R1. So we call it a read after write dependency or a raw dependency. So RA dependency is a read after write dependency. Which is also called a true dependence, because we first write and then we are reading it. So let's consider the pipeline diagram. So in the pipeline diagram, instruction number 1 enters the pipeline in the first cycle and subsequently it keeps on moving to the next stages in every consecutive cycle. So let's consider instruction 2. It enters the pipeline, the IF stage, in cycle number 2. So in cycle number 3, instruction 2 enters the operand fetch stage. That is when it needs the value of R1, right? So the value of R1 is needed in cycle number 3. But the problem is that when will instruction 1 produce the value of R1? Instruction 1, it will produce the value of R1 in the sense it will write R1 to the register file in cycle number 5, right? So we need the value of R1 in cycle 3, but it will be written to the register file in cycle 5. So basically we have an arrow, a big red arrow that is running backwards in time. So this is a problem over here, right? So instruction 2 will read incorrect values because in cycle 3 the value of R1 has not been produced yet. So it will read a value which is not right, which is not correct, and that will lead to wrong or incorrect execution. So this is something that should be avoided and that should be fixed. And what this translates to in a pipeline diagram is that the dependency between 1 and 2, particularly between the cells in which 1 writes the data and in which 2 needs to read the data. If we draw a line between these cells, then the line will flow backwards in time, right? It is flowing from cycle 5 to 3, and this is something which is not possible, something which is not feasible. As a result, we will read incorrect values if we follow this scheme. Alright, so let's define some terminology. Let's define the term a data hazard. So a hazard is defined as the possibility of erroneous execution of an instruction in a pipeline. So in specific, a data hazard represents the possibility of erroneous execution because of the unavailability of data or the availability of incorrect data. So in this case, it is what is happening is that in cycle number 3, if we go and try to read R1 from the register file, we will simply not get the right data. So we'll get incorrect data because the right data has not been written to the register file yet. So that will cause a problem, and that's called a data hazard, right? There is a possibility of an error. In specific, this is a RAW, a read after write data hazard, because we have two instructions where the first instruction is writing and the second instruction is reading. So the earliest we can dispatch instruction 2 is actually cycle 5, and here there is a problem. So basically, if we let's say have instruction 2 over here, if let's say instruction 2 enters the pipeline in cycle 5, in cycle 6 it will be over here and it can happily read the data from the register file. Alright, so the question is that for these 3 cycles we will not be able to push in any instruction into the pipeline, which will ensure that the pipeline is idle. This is a bad thing. So precisely we did pipelining to fix the problem of idleness, but as we see, for this specific pattern, which is very common, we will have issues. So basically for 3 cycles, we'll not be able to put in instruction 2 into the pipeline, and that's something which is very problematic. So we'll need to fix it. So there are other types of data hazards. So but these data hazards will actually not show up in our simple pipeline. So our pipeline is an in-order pipeline. So I'll discuss what that is. In an in-order pipeline such as ours, a preceding instruction is always ahead of a succeeding instruction in the pipeline. So let me explain what that means. So what this means is, so if I consider, maybe let me see a cleaner, there's a cleaner version of the pipeline diagram. So in this case, 1 is the earlier instruction, it is the preceding instruction, and 3 is a succeeding or it's a later instruction. So what we see in our pipeline diagram is that at all points of time, so let's say, let's consider cycle 5, at all points of time, the earlier instruction is at a later stage. It's ahead in the pipeline, right? And a later instruction, such as instruction 3, will always be behind instruction 1 and 2 in the pipeline. It is never allowed to overtake. So this property is called an in-order pipeline. So modern processors, however, do not use in-order pipelines. They use out-of-order pipelines that break this rule. So it is possible for later instructions to execute before earlier instructions. So this causes many kinds of complexities, and discussing out-of-order pipelines is clearly not within the scope of this course, but it will be a part of an advanced course. But in this course, we'll only look at in-order pipelines, and a lot of processors also do use in-order pipelines. It's not that they're not used. But nowadays they are mainly used for smaller processors, embedded processors, and so on, which where high performance is not really the key. We are more looking for power efficiency. So in all such processors which have in-order pipelines, and a preceding instruction, an earlier instruction, is always ahead of a succeeding or later instruction in the pipeline. So in such pipelines, we'll only have read after write hazards, but out of order pipelines can have other kinds of hazards like a write after read or a write after write hazard. So let us discuss what these two types of hazards are, write after write and write after read. So let us consider a sequence of two instructions, so where 1 is the earlier one and 2 is the later one. So both these instructions are writing to register R1. So instruction number 2 cannot write the value of R1 before instruction 1 writes to it. Otherwise, what will happen is that the final value inside R1 will become wrong. So we want instruction 1 to write the value of R1 first, and then we want instruction 2 to write the value of R1. So this is the sequence of actions, this is the flow of action that needs to happen. This will always happen in our case because we do not allow instructions to overtake each other. But in a pipeline which allows instructions to overtake each other, this problem can happen, but we need not be concerned about that. But nevertheless, what readers, listeners should know is that we can have a hazard of this type, which is a write after write hazard, where if we allow instructions to overtake each other, then erroneous execution is possible in this case. Similarly, we can have a write after read hazard. So let us consider this example. So instruction 1 is reading the value of R2. And then the later instruction, instruction 2, is writing to R2. So it's doing some computation adding R5 and R6 and it is writing to R2. So in our case, we will never have incorrect execution because we do not allow instructions to overtake each other. So instruction 1 will always be ahead. Say if this is the pipeline, instruction 1 will always be ahead of instruction 2. So that is the reason instruction 1 will always read the correct value of R2 and instruction 2 will then write to R2 at the end. However, so in our case, instruction 2 cannot write the value of R2 before instruction 1 reads it. In an out of order pipeline, it is possible. And this condition is a write after read hazard. So we have a read first and then a write. So this is called a write after read hazard. Again, it's not a problem for us. But if we allow instruction 2 to overtake instruction 1, then it becomes a problem. Alright, so what have we seen up till now? We have seen data hazards. So we have seen a write after read hazard which can definitely happen in our system. And so we showed a simple example and we showed a problem that can happen, that after instruction 1, if we immediately put instruction 2 in the pipeline, it will get a wrong result. So we need to wait for 3 cycles and then put instruction 2 in the pipeline. Then we looked at WAR and WAW hazards, which can happen in more advanced pipelines, not in our case. And RAR situation is not a hazard because you have one read and one more read after that to the same register. In an advanced pipeline also they can overtake each other, there is no problem. As long as the write is not involved, there is no problem. So these are the kinds of data hazards. So we can have another kind of hazard called a control hazard, which we shall see now. So let us consider an instruction of the form branch if equal. So if the equality condition is true, we shall branch to the label .foo. After that we have several instructions and then a long time later we have the label .foo and instructions after it. Now if the branch is taken, so let's assume that the branch in this case is taken. We will show that instructions 2 and 3 might get fetched incorrectly. So what will happen if the branch is taken? If the branch is taken, then the control should immediately jump to this point. And these 2 instructions should not be fetched or executed. But what we see in this diagram, so this is the pipeline diagram of a control hazard. Let's take a look at this in some detail. Alright, so what we get to see over here is that we have 3 instructions. The first instruction is a conditional branch, and after that we have 2 more instructions. So if the first instruction's condition is true, then we will jump to the .foo label. And if the first instruction's condition is not true, then we will execute instructions 2 and 3. So now, when I draw the pipeline diagram, what we see is that in the first cycle, in cycle number 1, instruction 1 enters the IF stage and it will continue. So the instruction 1, so the instruction 1 essentially does not stop. So every subsequent cycle it moves from one stage to the other. But the important point is in cycle number 3. So in cycle number 3, what happens is that a decision is made whether the branch is taken or not, because in cycle 3, instruction 1 is in the EX stage. So in the EX stage, the branch unit takes a look at the flags. In particular, it's a BEQ instruction. So it takes a look at the EQ, the equality flag, the flags.e actually. Flags, I should write it flags.e. So it takes a look at flags.e. And if flags.e is 1, then the branch is deemed to be taken, right? So the problem that happens is that at this point, if the branch is taken, then instructions 2 and 3 were fetched incorrectly. This is what it means. Because in the second cycle, when instruction 1 was in the OS stage, instruction 2 got fetched, so it entered the IF stage. Then in the third cycle, when we are making a decision about whether the branch is a taken branch or not, at that point the processor was busy in fetching instruction number 3 into the IF stage. So the problem that arises now is maybe towards the middle of the cycle or towards the end of the third cycle, we get to know that this is actually a taken branch. But by that time, we have fetched two instructions, instructions 2 and 3. We have fetched them from memory and they are in our pipeline. So if we do not do anything, then instructions 2 and 3 will simply continue down the pipeline and they will execute. And they will write 4 to R1 and then they will add R3 and R4 and write to R2. And clearly, these two instructions should not be executing. If they execute, the execution will be incorrect. So this problem is a control hazard in the sense that there is a possibility of erroneous execution. And the possibility arises because the two instructions fetched immediately after a branch instruction might have been fetched incorrectly and are definitely fetched incorrectly if the branch is a taken branch. So that's the reason if the branch is taken, there has to be a method of cancelling these instructions, killing them, such that they do not proceed down the pipeline, right? If they do, and if they are allowed to modify memory or to modify a register in the register file, then essentially our state will get corrupted and the program will be deemed to have executed incorrectly. And this is a situation that cannot be allowed. So this situation is referred to as a control hazard. Let me now explain once more what a control hazard is textually. So the two instructions fetched immediately after a branch instruction might have been fetched incorrectly if the branch is a taken branch. So these instructions are said to be on the wrong path, right? So basically these instructions, if they need to be cancelled later, then these instructions are known to be on the wrong path. So a control hazard, essentially, a control hazard represents the possibility of erroneous execution in a pipeline because instructions that are in the wrong path of a branch can possibly get executed and save their results in memory or in the register file. So it is our job to ensure that instructions which are on the wrong path, for example, these two instructions, instructions 2 and 3, they do not get executed if branch at instruction 1 is taken. So now let's come to a third kind of hazard. So we have discussed data hazards, we have discussed control hazards. So let's come to a third kind of hazards called structural hazards. A structural hazard may occur when two instructions have a conflict on the same set of resources in a single cycle. So this will not happen in our simple pipelines. It's not a concern for us. but it can happen in other pipelines. So it's good to know the concept in general. So assume that we have an add instruction that can read one operand from memory, right? If we have such kind of an instruction, so in such kind of an instruction, we'll have one of the operands which is coming from memory. Now let's take a look at an example in which a structural hazard can happen. So let's consider these three instructions, instructions 1, 2, and 3. In the first instruction, we do a store to the location 20 plus the address in R5. Then we have a subtract, and then we have the special kind of add instruction that we are talking about in the last slide. So here one of the operands is a memory operand, and that's going to be the second source operand. So reason that this code will have a structural hazard is as follows, that in cycle number 4, instruction 3 will be in its OF stage. So it will try to read the operand 10R3 from memory, so it will access the memory access unit. And similarly in cycle number 4, the store instruction will also be in its MA stage, right? It will also be in its MA stage. It will try to access the MA unit in cycle 4. And if the MA unit can process only one instruction per cycle, then clearly there is a conflict between instructions 1 and 3. And this is called a structural hazard. So a structural hazard is basically a situation in which two instructions try to access the same resource, or defined in a more generic way, if a resource can satisfy m simultaneous requests, but there are n requests that are coming into it, where n is greater than m, then we'll have a structural hazard because we simply do not have enough resources to satisfy all the requests. So in this case, the memory access unit can satisfy only one request at a time, but if two requests come, then one of them has to wait, and this is called a structural hazard. This will not happen in our pipeline, the reason being that we have designed it in such a way that we never have resource conflicts across stages. But it can happen in many other kinds of pipelines, so it's a good concept to keep in mind. So to summarize, the three kinds of hazards are once again data hazards. Data hazards, again, there are three kinds: read after write, write after read, and write after write. So in our pipeline, only the read after write hazard will happen, the rest two will not happen. Then we have control hazards, and control hazards can definitely happen in our pipeline. And we have structural hazards which will not happen in our pipeline. So given the fact that we have, an idea of what the hazards are, let's try to look for solutions to take care of RAW and control hazards. So this will be part of the next lecture. So the current lecture will end at this point.